Okay, a couple more examples here with the alternating series test. Okay, now it's a little rough here, but these are examples from the handout. And this is an alternating series you can see. And first thing would be to check if that limit, the 1 over root n, does that equal 0? And the answer is yes. Second, is it not increasing? So a sub n plus 1, is that less than or equal to a sub n? That's your question. Okay, well, let's show that it is. 1 over root n plus 1, we'll assume is less than or equal to 1 over root n. And let's show that for what n that's true. We're going to cross multiply. You'll have this. If we square both sides, we're going to have this. And these are both positive numbers, so this is fine. No problems. And this leads to this, which is true independent of n. So this will be true for all n. Okay. Now, got those two shown to be checked. Yes. So it is convergent by AST. Notice that the same series without the alternating characteristics there would not converge because it would be a p series with p equal to a half. So the alternating makes a difference. Okay, this next one down here, here I think we can see the first condition is pretty clear. And even though we don't work a lot with the factorials, that will head to infinity. So the fraction heads to 0. Check. Okay, second, again, is the a sub 1 plus n plus 1 less than or equal to a sub n? And we have to show that that's true. We believe it is, but you got to do a little bit of work here. So 1 over n plus 1 factorial, is that less than or equal to 1 over n factorial? Well, let's see, again, multiplying would give n factorial less than or equal to n plus 1 factorial. And I think it's pretty clear at this point that this is true. We don't really have, let's see, we can do a little bit more. Let's divide by n factorial here, like this. See where that takes us. This is 1, and this is n plus 1 times n factorial over n factorial. And factorials cancel, and then we're left with this. 1 is less than or equal to n plus 1. So this is 0. So this will be true as long as n is greater than or equal to 0, which it is for this. So this one is also convergent by the AST. Okay, one more down here. Again, limit n goes to infinity for this natural log of n plus 1. It's pretty clear that that equals 0 because the denominator heads to infinity. So the second question is, and I'm going to jump right into this, is 1 over natural log of n plus 2 less than or equal to 1 over natural log of n plus 1? Well, let's see if let's try something here. I think it's pretty clear that, I mean, a natural log is an increasing function. So 1 over the natural log would be a decreasing function. It's reciprocal. They do the inverse. Let's see if we can make this a little easier to see. Natural log of n plus 1 less than or equal natural log of n plus 2, both positive. So this would mean, let's see, what else can we do here? Well, it's probably good enough to stop here. Since natural log is an increasing function, we can argue that this would have to be true. As long as this is natural log itself is an increasing function, then this statement would have to be true for all n. In all n greater than or equal to 1 for sure. So we've got true, both conditions met. It's convergent by the AST. Without going into too much more work on this statement here, don't have to dissect it too much further. As I said, it's an increasing function, so n plus 2 is bigger than n plus 1. So, all right. So that's it.